In this video lecture, we'll talk about the Lebesgue measure, but not the Lebesgue measure on the real line, but now on the Euclidean space Rd. We'll start by defining what finite cuboids are, then define the sigma algebra of Borel sets in d dimensions, then state the theorem of existence and uniqueness of a measure which is called the Lebesgue measure on Rd. Then later on we'll define an appropriate algebra of subsets of Rd, define on that algebra a pre-measure as usual, because from there we can use Carathéodory extension theorem to get existence and uniqueness of the Lebesgue measure, and we conclude with some small examples that allow us to have a grasp on what the measure of some subsets of Rd are. So let's start by defining finite cuboids and Borel sets. A finite cuboid is a subset of Rd which is of this form. It is the Cartesian product of d finite left open, right closed intervals. If d equals 2, this is a rectangle, and this is what a rectangle would look like. So it is the Cartesian product of having as the first coordinate an interval which is left on A1, open on the left, closed on B1, and the Cartesian product of that interval with another one which is open on A2 and closed on B2. So we see here all the points in the interior of this rectangle, they belong to this set, and in the boundary, not all points, so this part of the boundary belongs to the set. This point also does belong to the set, but these 2 points or 3 corners do not belong at these sides neither. In 3 dimensions, we would have the Cartesian product of this interval, left, open on the left, closed on the right, this interval, open on the left, closed on the right, and this interval, open on the left, closed on the right. And when we take this Cartesian product, we get this, what we call cuboid, which you can see the projections of it to help you visualize. You can see if you project it to the left or towards the front or towards down, this will be the cuboid. 3 of its edges are in the cuboid. 1 of the vertices are in the cuboid. Other points, other edges are not. And also out of the faces of this cuboid, 3 of them are in the set and the other 3 are not. And for dimensions higher than 3, we just use our imagination. Now, when our sample space is Rd and we want to consider what's the natural sigma algebra to consider there, it is also called the Borel sigma algebra. So here's B for Borel and Rd, showing that it is the sigma algebra on this space Rd. And by definition, it is the sigma algebra generated by the class of finite cuboids. It is also the sigma algebra generated by the class of open sets. And this is the more general definition of Borel sets in general. We are ready to state the Lebesgue measure on the Rd. Here the theorem. The theorem says there exists a unique measure that we call M on this space Rd with the sigma algebra of Borel sets, such that the measure of a cuboid is exactly the product of the dimensions of that cuboid. So in dimension 3, it is, as we would expect, the product of height, length, and depth and width. And in dimension 2, it would be height and width. So it is just the product of its dimensions. This is the volume in dimension 3. We also call it volume or hypervolume in dimensions higher than 3, and area in dimension 2. We call this unique measure the Lebesgue measure.